Well, hi everybody. Today we have Reniers with us. He's the head of the section of environmental fluid mechanics in the Department of Hydraulic Engineering in the Delft University of Technology. And he would talk about modeling wave impacts on complex coasts. So welcome.
Thank you. Well, thanks for being here. I dressed up Miami style. I don't know whether this is also Mallorcan style, but this is typically not how I walk about in the Netherlands, which is way more formal. So I assume that everybody would be relaxed. So to give you a little bit of a background, I did my PhD at the University of Delft in '99, and then I did a postdoc of 3 years in Monterey, California. That's where I worked on rip currents mostly. They have very nice beaches, for those of you that Iris has been there, for example. They have quasi-permanent rip currents, and because of that, there's a lot of attention for it, and also because of, no problem, come on in, potential drownings. And that actually is where I got very familiar with field work, because people tend to avoid areas where it's dangerous. So hence, that was one of the sites where we could still make progress in using field work. We used human drifters, GPS, etc., to get a good idea of the flow circulation, and always in combination with modeling. Then I went back to the Netherlands at Delft University, and I started teaching. I teach ocean waves. And I developed, along with some other colleagues, we started working on morphodynamic modeling. So trying to couple hydrodynamics with sediment transport to look at the morphological evolution of the beach. Initially, I was using it mostly to look at the generation of rip channels, but it also led to the development of XBeach, which is something that I'll discuss today. Then after 4 years, I decided that the Netherlands was not a good place for me. So we left, and then I spent 7 years in Miami. And that's where I worked at the Rosenstiel School, which is a marine school. So I actually worked with a lot of marine biologists, not only at the Rosenstiel School, but also at the California coast. So I have some experience with working with marine biologists, but also oceanographers and chemists and geologists. But there was definitely a lack of people with my skills, so I was sort of the only one that knew something about what happened if you get close to the coast, which is where my expertise is. For personal reasons, we moved back again, and I've been back in the Netherlands for 3 years now at the section of environmental fluid mechanics. So my talk is about the work that we've done in I think it covers about 7 years or so, on the wave transformation on coasts. So it's particularly to look at how the waves go from deeper water all the way to the waterline, and then with emphasis on what I will explain is infragravity waves and what we call very low frequency waves, but I'll get to that in a minute. So there are some equations in it, not too many, but if you have questions, then just raise your hand and don't wait until the very end, because then it'll be way past and it won't be relevant anymore. So if you have questions, just feel free to ask. So the presentation is actually work that's I'm presenting, but most of the work has been done by these people that are here at the bottom. You may know some of their names. So it's a mix of people at the university, but also Deltares. Let's say Kurt is actually at the USGS in the United States. Nathaniel Plant is also at the USGS, as is Dave Thompson. Jaap van Tiel de Vries, sounds like a really Dutch name. He's one of my former PhD students who worked on it. Dano Roelvink is the originator of the XBeach model, so he's probably the best well known. And Ab van Dongeren, people always mix us up because we look kind of the same. We also used to share an office, both wear glasses, so and our names are very similar, Ad and Ab. But he's focused more on coral reefs lately, and I know Hanno is interested in coral reefs, so I have a presentation that also includes coral reefs. So the whole idea is that we need to protect our coast. That's, I mean, being in Dutch and from the Netherlands, as you know, most of our country is actually below sea level, so we need to make sure that the water doesn't come in. And of course, this happens at extreme conditions, so you need to know something about how the waves actually make it towards the coast. Now, in the Netherlands, a lot of the beaches are sandy, but I did a little tour around here in Mallorca, and some beaches are sandy, but lots of beaches are not. So if we want to do this, if we want to apply this to other coasts, we need to understand other systems. So that's what this talk is about. So we want to develop process-based models, so we want to make predictions based on the processes, but they can incorporate more complex coasts, so including vegetation or other things. And then to do this, we need to understand how things work, and then we need data to compare it with, so to make sure that we did it right. Well, this is a quick overview of different types of coasts. This is in Monterey, where we did the rip current experiments, for example. That's a typical sandy beach. This is a coral reef beach. This is actually an Arctic coast with permafrost. Cliff erosion. Who knows where this is? This is a question. Yes, Calameo, yes. So why is that here? Because this actually has vegetation. So this is a coast with vegetation. And this is somewhere in England where they have lots of gravel beaches. But I also saw that at Bayambalapoor, what's the place again? They also have gravel beaches. So this talk, I'll mention something about modeling on, let's say, traditional sandy coasts. Then I'll progress to vegetation, and then I'll finish with coral reefs. Okay, this is a bit of a busy slide, but this is one of the key slides. So what you see here is a depiction of the processes that we are trying to incorporate. The thin line that I made over here is supposed to represent the individual waves. Those are the waves that you see at the beach. So if you go to the beach, those are the waves that you see. This thick line is the envelope. The envelope actually is an indicator of the groupiness of the waves. And in fact, if you go to the beach, you'll see that not every wave has the same height. It actually varies in height. And that variation in height we call groupiness. And because of this groupiness, you also have a variation in the forcing. So every wave actually exerts a force on the water. But what happens is that the bigger waves have more force than the smaller waves. And as a result, the water actually gets pushed away from the big waves, and it goes towards the smaller waves. And this is what we call bound long waves. So this dashed line is a bound long wave, and it actually has a trough where the group is highest, and it typically has a crest where the groups are low. And this travels with the wave groups. Now, as the waves get closer to the coast, they start breaking, and then this groupiness disappears, and that means there's no longer any forcing of these bound long waves. And they get released, and they return as free long waves. It just means that if they come in, they travel with the group velocity, and if they go out, they travel with the free wave velocity. In this case, because they're long, it's the square root of GH. And then we couple all of this to sediment transport. So typically where the waves are high, you have a lot of sediment in motion, and that's then transported by the waves themselves, but also by the mean currents and the infragravity waves. And then XBeach, which is the model that we're using, also has a module in it that accounts for avalanching. So if you have a storm, there's a surge level, so the wind pushes up the water. These infragravity waves, they run up the beach, and then the sand actually slides down in an avalanching motion. Now, this is to remember, so I consider 3 different time scales. So the sea swell time scale, so those are the incident waves, typically shorter than 25 seconds. Then I have the infragravity time scale, so that's between 25 and 250 seconds. And then the very low frequency time scale, which is longer than 250 seconds. We can run this model in 3 different modes. We have a stationary mode, which is, I don't know how many people are familiar with modeling of waves, but basically you have a constant wave height that is propagated towards the coast. It's a typical approach for ROMs or Del3D and Swan. And you don't see any variation, but you do see this black line is a mean water level where the waves are breaking. They push the water up, and that's where you have a setup. This is the traditional XBeach mode, which we call surfbeat. And then you see that we're modeling the groups. So this dark blue is the envelope again. And because it varies, you see these long waves that are traveling with these groups. They run up the beach and they reflect. And then the third mode is what we call the non-hydrostatic mode. And then you resolve everything. So that just basically does everything. This is the fastest. This is medium, and this is the slowest. So it's always, because ideally you would do everything here in this, and then you have everything. But yeah, that's not feasible because it takes too much time. Okay, so a typical application for XBeach is this, which is in the Gulf of Mexico, Santa Rosa Island, where we had a hurricane, I think it's Hurricane Ivan. It's based on the work that was done by Robert McCall. The hurricane came through in about 40 hours. The grid is about 3 kilometers in the alongshore, in the cross-shore, and 1 kilometer in the alongshore, and it covers the barrier island. So the Gulf of Mexico is here, and the back barrier bay is over here. And if you want to do proper modeling, you need to know the surge level. The thing with hurricanes is they tend to destroy everything, so you don't really know what the water level is. So we use the model, in this case Del3D, to calculate the surge level. So that's a combination of wind and tides. Then we used Swan to calculate what the maximum wave heights were during that time period. And so that came down to about 6.5 meters, and the period in the Gulf of Mexico under hurricane conditions was about 20 seconds. And the objective was to look at the overwash and inundation of this barrier island. Now let's see whether I can get this to. Yep. The grid resolution. Actually, the grid resolution varies. So because we're modeling the infragravity waves, they have longer length scales in deeper water. So the grid resolution in deeper water is larger, so that could be like 25 meters or so. And then it gets to a couple of meters close to the coast. So overland is in that order. And in the alongshore direction is typically 10 meters or so. In the alongshore direction, the grid spacing is about in the order of 10 meters. And what you see here is actually a snapshot of the surface elevation, but this is the surface elevation of the infragravity waves. So this is not the individual waves, this is just the infragravity waves and the mean water level. Waves are coming in from the Gulf of Mexico. This is the barrier island. And below here is actually a depiction of the sedimentation and erosion. So red is erosion and green is sedimentation. This shows the surge level. So this is tide and wind. And this is probably very difficult to see, but the green line is the wave direction. So this is more at this point in time. It's more or less shore normal. And the wave height is about 4.5 meters. So it's not at the peak, but it's pretty high. And I'm showing this because this is at the time when the overwash starts. Okay, let's see. So what you see is infragravity waves that are generated by groups. They're going in, they reflect off the beach. So that's why you also see all these reflections that are coming back. But because there are certain parts of the island that are lower, the infragravity waves run up and start overflowing. And this is where we talk about overwash. So now there's water overflowing from the ocean side. Well, the Gulf of Mexico is not an ocean, but let's say the Mexico side, the Gulf of Mexico side, towards the back bay. And because of that, there's also sediment transport that goes from the coastal side into the back bay. And this is actually one of the mechanisms where these barrier islands can survive. Because they can cope with sea level rise by moving the sediment from one end of the island to the other one. It's called rollover. Then if you look at the differences between models, the model predictions and the observations, this is the model prediction, and this is the observation based on LiDAR, pre and post hurricane. If you just focus on the area where the LiDAR has data, then it actually looks very good. However, there was one caveat, that to make it work, we needed a transport limiter. Because without this transport limiter, the island would erode too much and basically would disappear. Whereas in reality, we know that this is not the case. Yes?
I was thinking the model with the dry part.
Well, it has a drying and flooding procedure. So if the water level reaches a critical height, it inundates the next cell. So by doing so, you can actually inundate the dry part of the land. Yeah? Okay. So why would you need a transport limiter? And this is, I think, where it gets really interesting, because you can have all sorts of reasons why you need a transport limiter. Why doesn't sand transport like you expect it to be? And I think especially on land, the sand has been there, it's been affected by the wind. It may have an armoring layer, but it also has likely a lot of vegetation. So that brings me to my next subject. What about vegetation? I came back a couple of months ago from Indonesia, where we have an experiment that looks into mangrove forests. This is a part of the coast that is heavily eroded. The mangroves have more or less disappeared because of aquaculture. And because of that, of course, the coast is receding and threatening people's houses. So what we're trying to do is trying to figure out, can you restore these mangroves? And why are they important? Well, this is to give you an idea that if you have vegetation, so in this case it's the roots of the mangroves, you can see that a lot of the energy of the waves is actually dissipated through the interaction with the vegetation. And because of that, it can help in protecting the coast. So if we can come up with a system where the vegetation attenuates the wave, so it makes the wave smaller, then it also will affect things like the setup, but also infragravity waves, runup, and therefore coastal safety. If the conditions are such that the seedlings can settle, you can actually get a positive feedback mechanism. So now the seedlings can settle and you can have more mangroves, which is ultimately what we're after, because that way you can have a progressive coast that is protected. Because of that, you can also retain sediment, and ultimately you can reduce the coastal erosion. So that all sounds very good, and that's sort of the ideal that we're looking for, provided it works. So, and I said, provided we understand how it works. Because if we don't understand how it works, and especially, let's say, in more extreme conditions, then you may get the false sense of security. So you may think you're safe because the waves are smaller, but that's during moderate conditions. What happens if you have extreme conditions? In that case, the vegetation may actually get uprooted, or you can have stronger circulations that lead to higher water levels. So we really need to understand better how it works. And for that, we developed some more modeling tools. So this is based on the work by Arnold van Rooyen, who's doing his PhD in Australia at the moment. I think Iris gave a talk not too long ago about the physics of interaction of waves and vegetation. Is that right? Oh, not here. Oh, okay. Okay. This is just to give you an idea of how it works. So we have, I made a depiction of the waves. So the waves are propagating from left to right. C is the phase speed. And this is Posidonia, sort of. And for a given stem, you can calculate what the forces are of the waves on the plants. Now, if you assume that these plants are not moving, so they're rigid, they are fixed in height, etc. If you know what the drag coefficient is, which is really unknown, that's a thing that needs a lot of attention. But if you have the diameter, the density, then you can approximate the forces on the vegetation by this formulation that was derived by Dalrymple. So these are all parameters, but the key element is this part, which is the velocity. That's the total velocity. So if you have the velocity, you can calculate the forces on the plant. Now I come back to my time scales. So in the beginning I said I'm making use of different time scales. So I have the incident time scale, I have the infragravity time scale, and the very low frequency time scale. But there's also a mean time scale. What I do here is I have the incident band, so these are just the individual waves, and I get all the low frequency waves, so infragravity and VLF in here, and I have a mean time scale. And I'm going to substitute that into this drag force. Then if I do that for the short waves, all I'm doing is I'm taking this part of the velocity, I substitute it in this formula, and then you get this. But all our modeling efforts typically average over the short waves. So this overbar, that means that it's wave averaged. That's what, this is also what we do, for example, in Delft3D or ROMS or WAM and WaveWatch 3, everything is wave averaged. The funny thing is that if you have linear waves, and I always tell people there's no such thing as a linear wave, but we all use linear wave theory to say something about waves. Linear waves are just sinusoids. If you have linear waves and you would average, then by definition you get 0. So wave averaged, the forcing by the incident waves would be 0. But if you have nonlinear waves, for instance Stokes waves, and I'll show an example in a minute, then this contribution is actually positive. So then you have a wave average contribution to the forcing. And then in addition, you have the other components which are related to the mean components and the infragravity. Okay, so this is standard, except that people typically don't take the infragravity, but this is definitely different. And I'd like to show you what the differences are if you include it or not. So this is a little short intermezzo about how you can get to the nonlinear shape of the waves. You don't have to remember any of this, but hopefully I can convince you this is true. Yeah? You can use different theories. So Reniers and Fenton used the stream function theory to construct the velocity of the waves. And what you have to remember is that the velocity of a nonlinear wave is not made up of a single harmonic, but it has multiple harmonics. So in this case, you take 8 harmonics, and they have a decreasing amplitude. And if you add them all up, let me show you the result. Okay, so if they're all in phase, so if you take all the cosines, then you get a Stokes wave. So for those of you that are, if you go to the beach and you see Stokes waves are defined as high crests and shallow troughs. This is typically the wave shape that you see before the waves are breaking. If the waves are breaking, then they tend to look like a sawtooth wave. This is at the break point, so this is where you have the bore. So with this formulation, you can actually calculate what the nonlinearity is of the wave and the shape of the wave. And it's determined by the local wave height, wave number, and local water depth. So based on this, you can calculate what the phase is, the weights, and therefore you can calculate what all these different harmonic components are. So with this simple approximation, you can calculate the shape of nonlinear waves. Right? Once I have that, I can use it to calculate the forces on the vegetation. So in a 1D setting, I have the continuity equation here, which is the surface elevation, the velocity, and the local water depth. and I have the momentum equation. What I want to point out is that if you ignore, let's say, the velocity, so we look at steady state and we ignore, so this is 0, we ignore the nonlinear terms of the velocity, but this is all wave average, then you see that there's a balance between, this is the setup, and bottom friction, wave forcing, and the forces on the vegetation. No questions about this? This is all clear? I think what you want to get away, what you would like to get out of this is that the waves are pushing against the water, and they're pushing the water level up towards the coast. The vegetation is actually pushing back, because that also experiences forcing. The bottom friction will ignore. So what you then have is a balance between the pressure that is generated by the slope of the water and the forces because of vegetation and the waves. So if this term is non-zero, then you expect to have an effect on the mean water level. So what we need, I did mention a few equations. What we need is we need to know the wave forcing and the vegetation forcing. The wave forcing is dependent on wave propagation. So that's the group velocity here. So this is the energy balance. So this is the wave energy. The time variation in wave energy is a function of the gradient in the flux. This is just a flux condition. But then it has sinks. And this sink is related to the braking. And this sink is related to the fact that there is vegetation. Because if you have vegetation and there's forces acting on the vegetation, then that means there's work done by the waves on the vegetation, and that leads to a sink. So this is something that Mendes and Inigo Losada worked at. So if you know the characteristics of your vegetation, and again your drag coefficients, then you can calculate what this dissipation is. And I'll show you some examples to give you a feel for it. Okay. With that wave energy, you can also calculate what the forcing is because of by the waves. All right, so those are the equations, and now I'll try to explain it. So this is a comparison between the surfbeat model, so XBeach model, and observations. The black line and the black dots is the scenario without vegetation. So this is the classical wave propagation. So what you see is the waves are coming from, this is all at scale, but so the waves are coming from offshore, they shoal, they get a little higher, and this is where they start braking, then they dissipate a lot of energy because of braking, and it goes towards zero. So the solid line, the solid black line is the model, and the dots are the observations. And that's not new, that is something that, that we've worked on a long time. But if you include vegetation, that's over here, then what you see is that outside of the vegetated area, of course, it behaves exactly the way the other one is working. But then once it hits the vegetation, the dissipation by the vegetation is dominant over the dissipation by braking. So what you see here is that the wave height is decreasing rapidly compared to the case without vegetation. So vegetation actually helps in attenuating the waves. So it makes the waves smaller. The model is the solid line, and I have two versions of the model. I have one version of the model where I ignore the nonlinear shape of the waves, which is I think the dash line, and I have a version where I include the nonlinearity of the waves, so the wave shape. Now for the wave transformation, it doesn't make any difference. This is the instant wave. This is the infragravity wave. So these are the long waves. Without vegetation, you get this black line. With vegetation, we get these yellow lines. And the model suggests there's significant dissipation. But as you can see, there's no data. It's actually one of the reasons I'm here, is trying to get data to confirm or or show the opposite, that infragravity waves are damped differently from incident waves. So that's one of the things that we're trying to figure out here. Now this bottom plot looks a little messy. Again, the black line is the model without vegetation, and the solid dots are also without vegetation. And what you see is there's a set down, so the water level actually goes down before the waves start breaking, and when the waves start breaking, you have set up. And we know that breaking waves pushing hard against the water put the water level up. This is what we call set up. That's also one of the things that makes it dangerous during storms. If you have big waves, that the mean water level gets high enough to inundate and you get overwash. If you include vegetation and you include the wave shape model, then you get this solid yellow line. And basically this setup is disappearing. And that's because there's the balance between the wave forcing and the vegetation forcing. So this suggests that if you have vegetation, the setup, so the difference between this and that, is much less, and hence that would really help in creating additional safety. If you ignore the nonlinear shape of the waves, then you see that the setup increases again. So the shape of the waves, the nonlinearity, is very important. This is to give you an idea about the differences with and without vegetation. So this is with vegetation. Oh, sorry. This is with the wave shape model, and this is without the wave shape model. It's all with vegetation. And you see that without the wave shape model, the setup, so this is the wave setup at the shoreline, is much larger than in the scenario where you don't have vegetation. So this tells us that with a larger vegetation extent, so the more Posidonia you have, and the closer it is to the beach, the better the safer you are. That's the message. And because it's a big difference, the wave shape is actually very important. You still with me? No questions? Oh, okay.
About the experiment.
Yeah.
Were made on lab.
Yep.
And the density of the vegetation.
In the lab?
Yeah, I guess it may have different densities.
Well, we didn't do the experiment, so we used the experiments by Wu.
And we don't know if there's, I guess there's a difference in between densities and vegetation. There is a limit where it
They
starts.
show a constant density.
Yeah, and this is typically with wooden sticks and.
I can imagine there is a limit because you don't have to. It's not anymore involved on impact or vegetation. You need a minimum density.
Oh, okay.
So normally
Yeah.
the experiment you have like a big density of vegetation.
Yeah. So the.
And you can imagine if you put that on a beach like Reniers and you make the experiment with plants or vegetation, it's going to be hard to find results, similar results because of density of vegetation. Less than
Yes, that's true, but that's what you see here. So instead of having there's different ways of doing this. So you can make the vegetation denser. Of course, then you have more interaction with the vegetation. But you can also start it further away from the beach. So basically, the area over which the waves are acting with the vegetation, you can make that longer. Yeah. So there's different ways where you could experiment with this. So what you see here, basically, if you increase the vegetation field, the setup is getting less and less and less. If you have a very short vegetation field, it's almost identical to what you have without. So it's the vegetation density. It's all of that is important. Yep. Yep. How am I doing on time? Yeah, I'm talking too much. That's always my problem.
It's okay. 30 minutes, so you have a little bit more.
All right, let me know when I need to stop. So this is actually something different, which is related to coral reefs. This is a study that's being done by Stuart Pearson. And okay, I'll forget. I'll skip this. Why this is important, but everybody knows that with the sea level rise and the changes in wave conditions, these atolls get more and more vulnerable. It affects not only the safety but also the freshwater requirements. So there's a lot of interest in trying to see whether we can come up with an early warning system for these atolls. And so what we're doing is instead of and there's very little known about these atolls, and they all have different shapes and different reef shapes and etc. So instead of doing specific calculations for a given atoll or a given reef, we did a range of computations where we varied the different parameters. So a typical reef morphology has a beach, a reef flat, reef crest, and then the forereef, and then the coral. The coral actually, like vegetation, affects the roughness. There's also an added complexity that because of bleaching, coral can die, and it actually will affect the roughness. So there's not only sea level rise, but also the bleaching of the coral can be important in coastal safety. So what we did is we did 190,000 XBeach simulations in the non-hydrostatic mode. So we resolve the individual waves, and we vary the width of the reef flat, the height, the wave steepness, the reef front, the drag coefficient, and the slope of the beach. All of that is being varied. And we look at the run-up. So what we're interested in is what is the highest level of the water here, because that determines whether or not there's going to be overtopping, and because if there's overtopping, then you have inundation and then saltwater intrusion, etc. So that's the key parameter. To give you an idea, again, we make this distinction between incident waves, infragravity, and VLF waves. So if you have a small wave group, it comes in, it shoals, so it gets higher, and then it starts breaking on the reef, and then it dissipates over the reef flat due to mostly dissipation due to bottom friction. And as I told you, the waves, when they break, they push against the water. So where they break, they push it up, and you get a setup. But if you have a big group, then they're higher, they push harder, and because of that, the setup gets higher. So by having these groups of waves that are coming in, this setup is also going up and down. So that goes at the time scale of the groups, and that's what we call a dynamic setup. So this dynamic setup has contributions of the groups at the infragravity scale and the very low frequency scale. So again, sea swell, 25 seconds and shorter, infragravity between 250 and 25, and anything longer than 250 seconds we call very low frequency. Then you can run these 190,000 calculations, and you can calculate what the contribution is to the run-up. So this R2% is the run-up measure, and this is let's say the tidal elevation. So with increasing tide, of course, the run-up gets higher because the tidal elevation increases. And these are the different contributions. This is the setup, VLF, infragravity wave, and the incident waves. You can do that as a function of the wave height. Of course, with increasing waves, you get increasing run-up. You can look at the steepness. Increasing steepness actually decreases the run-up. Friction coefficient, small friction coefficients, higher water level. This is not that important. This is an interesting one where you see that if the reef width is decreasing, if it gets smaller, you can get suddenly much higher run-up levels. So we looked into what causes this, or what is the potential cause, and could this be explained by resonance? And the reason to look into resonance is that others, let's say, in comparison to regular waves are being attenuated; they are dissipated by the reef. But resonance, actually, you can have wave conditions that are enhanced, and because of that, they're very difficult to predict, and they can lead to very big wave forces and accordingly destruction of property. So it's really important to know when you get resonance or not. For a given reef configuration, you can calculate what the resonance frequency is. So this is f sub n, which is a function of the depth over the reef and the width of the reef. And if your wave forcing over here has the same frequency as the resonance frequency, then you expect to have a lot of extra elevation. And that can happen because of the forcing itself. So the waves, as the waves are longer, you can have more forcing. If the height of the reef increases, that means that the resonance frequency of the reef increases. If the reef gets shorter, the resonance frequency increases. And because the typical, let's say, width of the reef, they require low frequencies, waves to excite the resonance frequency. That's also why for the very long reefs you don't see any resonance, but if the reef gets shorter and shorter, then the forcing and the resonance frequency get closer to one another. So what we did then was take these 190,000 computations and compute the mean frequency divided by the resonance frequency, and then we have a ratio of the significant wave height at the very low frequency scale and the offshore, the incident wave height. And if it's on this red line, that means it's resonance. And what you see is that if the forcing is indeed at the resonant frequency, you see a lot of amplification of the incident waves. So this suggests that resonance is there and it can be important. So, but we're still trying to figure out the details of it. I'm almost done, okay? I'll leave this for now. So the key is that what we really need is data. We need validation of our models. So we have models. I showed you comparisons with the lab. The lab is definitely not the same as the field. So there's lots of scaling issues. So any data that we can get to look at the conditions in prototype is really going to help us. And that holds for the reef, but that also holds for the vegetation. So both of these need additional data. And there's lots of other processes that are important, but I think that the key is that if we have more data, we can make it better. That's why I'm here. These are some pictures of last week, where we deployed these wave droids at Cala Mior. 2 wave droids, one at deeper water, one at close to the coast, coinciding with AWACS and vectors. And with that combination, hopefully we can get a handle on the attenuation of the incident waves, but also particularly at things like infragravity waves. And you probably recognize these people. So. Thank you. That's it. Yeah? I apologize that I took too long.
Thank you, Ad. It was a really nice talk. Do you have any question for him? Yeah.
I have 2 questions. The first one is just a clarification. So you introduced the vegetation is a non-linear dissipation in the wave equations. Is that correct? So just put a force which is proportional to the square of the velocity of the waves. Is that correct?
Yeah, that's the force, and then the work done by the force that leads to the dissipation.
Exactly. So it's non-linear. There's a non-linear dissipation. Right. Excellent. And the second question is, when you introduce the vegetation in the model, you introduce it as an homogeneous density. Is that correct?
Yes, for now.
For
yes.
now, yeah?
Yeah.
And do you think you put, let's say, non-homogeneous distributions of density? Would that change the dissipation? How do you think?
Yeah, it would. In fact, that's one of the previous slides, I think. So there's the density not only can vary in space, but also in the vertical. So this is the thing with the mangroves, for example. Depending on how high the water level is, you have a different canopy that the waves encounter. That is something that at the present, we're not taking into account. So for us, we have a height of the vegetation, but we assume that the density is independent of the depth. But in reality, that's not the case. But the thing is, there's so many other things that are unknown. Yeah. So, but it's something that we're looking into, and I think if we really want to get a handle on it, we should also look at the flow within the density. Right now, we're using the flow, at the top of the density layer, at the vegetation layer. But really, if you start looking at dissipation, it's not the velocity at the top; it's the velocity within the canopy that determines the dissipation. But yeah.
This was my question. I mean, do you really need the near bottom velocity, right, to solve the dissipation?
Yeah, I think if you want to do it properly, then let's say for Posidonia, it's the near bed velocity. This model, this XBeach model, is a depth average model. It doesn't really resolve the vertical structure of the flow. So there's limitations to the modeling approach, and I think there's many avenues that we can explore to make it better. But then, because there's still, this drag coefficient, for example. We have a drag coefficient that's in there, which is around 0.4. But it really depends on the characteristics of the vegetation. If you have vegetation that moves, it's very different from something that is rigid. We are assuming that it's all rigid. So there's many aspects that can be improved.
So for the sediment transport program, then when you get the vertical velocity, the average vertical velocity, you get the bottom velocity by using again the linear theory.
If it's about the stirring of the short waves, for example, then yes, then we use linear wave theory. Yeah. But let's say if you have so during storm conditions, the waves stir up a lot of the sediment, but then the flux is actually determined in a large part by the return flow. In the return flow, we assume that it's uniform over depth, whereas we know in reality it actually has a vertical structure. So you could use a local model to account for that, or use a different model, like a 3D model. Yeah.
This is a little bit out, but I would like you to tell us if you could make some difference about when to use a XBeach model or the Del 3D model, depending on what you want to study, like Calamity. If you want to study this beach, like more.
Well, actually, I think I'm out of the sight of the camera for 90% of the time. So,
why would you use Del 3D instead of XBeach model or?
Yeah, well, so it really depends on what you're looking at. Let me start with this scenario where, if you're interested in for example, in the transport of pollutants or material or larvae or plankton. In that case, you probably want to have something that has resolved the vertical structure of the flow, because depending on where the pollutants are, you get different transports. So in that scenario, I would definitely choose for a 3D model like ROMS or Del 3D, because XBeach will not give you the vertical distribution of the flow. If you're interested in beach erosion during extreme conditions, then I would say take XBeach, because it's designed for that kind of.
Bar movement, for example. You want to study bar
Yeah, if you want to study bar movement, I would use neither. But there's another model. It's called Unibest TC. Yep, which is specifically developed to look at to predict long-term bar evolution, and that's at least a model that I know of that really works. So, but that's a 1D model, so it takes a transect and it can predict the bar evolution. Yeah. No more questions?
Anyone else? Oh.
Feel free to address me afterwards, or I'm here until next Friday.
Okay, thank you very much for the
Thank you.
talk.
Thank you.